Welcome to another episode of Wave FEA Tutorials. This is your host Mac, and today we are going to talk about the ways to get temperature distribution based on applied thermal loading from nonlinear steady-state heat transfer analysis, and then use the temperature distribution to determine the effects on the model due to thermal expansion. The various topics that will be covered in this tutorial are heat flux boundary conditions, convection boundary conditions, setting up materials for heat transfer analysis, and setting up thermal loads with the output from previous analysis. We will be running the nonlinear steady-state heat transfer to get the temperature distribution for input, which serves as load from output in linear static analysis, which in turn will be used as thermal stress analysis. Let us jump right into the tutorials and define the deck for nonlinear steady-state heat transfer analysis. Let us first define the units of measurement, the English system. Let us now define the material. Click on the material on the command manager, change its name to 4130 alloy steel, enter the Young's modulus as 3 to the power of 7, let the Poisson's ratio be 0.32 and enter the thermal expansion coefficient as 7.5 to the power of 6. As we are conducting nonlinear steady-state thermal analysis, we should define the thermal properties as well. Also check the thermal checkbox and define the specific heat and thermal conductivity as 40.53 and 0.00055555 respectively. We can now create the physical properties. To do this, click on Idealizations on the command manager and make sure the material 4130 steel is selected and click OK. Let us now define the mesh. Right click on the mesh model in the analysis tree, define 0.1 inch under the element size, check the continuous meshing option, change element order to linear, and finally click on generate mesh to discrete the model into elements and nodes. Let us now set the analysis. In order to do this, right click on the analysis on the analysis tree, select nonlinear steady-state heat transfer and ensure temperature and SPC heat flow options are checked. The loads have to be defined now. Click on the load in the command manager, change the name to NLSSHT, set heat flux from type menu, select the inside surfaces for the flange and all the 4 tubes that make up the whole. After selecting the inside faces manually, enter 0.035 under load definition. To visualize the load, increase the density under display options and check preview to confirm the applied load. Let us now define the convection load. Click on the load in the command manager, change the name to convection and select convection for the type of load. Right click on the selected entities, select the faces and also manually select all the exterior surfaces of the tube. Enter the temperature as 70 degree Fahrenheit under the ambient temperature and set the coefficient value as 3.858 to the power of -5. Click OK to confirm. Let us now define the initial temperature. Click on the load in the command manager, change the name of load to initial temperature, select the initial condition from the drop-down menu type and set it to 70 degree Fahrenheit. Now that the deck for nonlinear steady-state heat transfer is ready, we can run the analysis in Nastran. Click on Run in the command manager to run the Nastran solver. With this, we have conducted the nonlinear steady-state heat transfer analysis and obtained the temperature distribution for the exhaust manifold. Let us now set up the thermal loads. To do so, right-click on the analysis 1 and duplicate it. Rename it to thermal analysis. Right-click on the thermal analysis and click Edit to change the analysis type to Linear Static Analysis, and under the title, enter Thermal Stress Analysis. A notification will be displayed stating that the analysis type is not valid with its current load and invalid loads will be removed. Click OK to confirm. We can now define the temperature loads. Select the From Output tab from the drop-down menu type and rename the load to Temperature Load. Under Load Definition, select the output FNO file which has the temperature distribution data. To define structural constraints for the model, click on Constraints in the Command Manager, change the name to Structural Constraint, select the bolt hole surfaces and constrain the hole surfaces in all the directions. Let us now define the new sliding constraints. To do so, click on the New button in the Constraint dialog, change the name to Sliding Constraints, select the surface on both the flanges facing away from the tubes and check all the degrees of freedom except Tx. This will allow the nodes on the surface to slide about the plane they are in, but will not allow it to penetrate it. We can now run the analysis in Nastran and then check the results. To check the deformations, right-click on the displacement under Results in the Analysis tree and click Edit. Click Visibility Options tab to hide all unwanted edges and view the constraints. Click on Deformation Options tab and click Animate under Plot tab and notice how the model will animate. To check solid von Mises stress, under Result Data, change the drop-down to Stress and under Type, select Solid von Mises stresses and click on Display. Click Animate to check the animation for von Mises stresses. In this tutorial, we have learnt heat transfer and thermal stress analysis of an exhaust manifold. Thank you so much for joining us today. This is your host Max signing off. For more information, visit our website www.wavefea.com. You can also opt for a 30-day free trial of Wave FEA software by registering with us on our website. We will be back with more features and updates from Wave FEA. Thank you.